Welcome to The Explainer. So today we're looking at a story that feels, incredibly modern, but it actually spans 70 whole years. We are about to unpack the massive, dramatic evolution of artificial intelligence, taking you all the way from some surprisingly old early theories right up to the generative AI tools we're all using today. It's kind of wild to think the tech behind your modern chatbot has roots older than the microwave oven. Let's get right into it.
I mean, it feels like ChatGPT and modern AI just dropped out of the sky over the last couple of years, right? But did it happen overnight? No way. Absolutely not. The true history of artificial intelligence is an incredible 70-year roller coaster ride, and it is completely characterized by these dramatic peaks of extreme optimism followed by incredibly dark valleys of deep freezes. It's really a story of broken promises, massive scaling failures, and ultimately, some pretty stunning triumphs.
Okay, let's dive into this. This whole journey officially kicked off way back in 1955. The actual term artificial intelligence was coined in a proposal for the Dartmouth Summer Research Project by four pioneers: John McCarthy, Marvin Minsky, Nathaniel Rochester, and Claude Shannon. They launched it as a formal academic discipline during the summer of 1956. But here's the kicker. They founded it on a remarkably hubristic belief. They genuinely thought that every single aspect of learning and human intelligence could be so precisely described that a machine could easily be made to simulate it in just a couple of months. That massive early hype perfectly anchored the very first peak of AI optimism. Which brings us to Section 1, Symbolic Logic meets Reality.
So, how did those early scientists actually try to build these intelligent machines? And what philosophical roadblock did they immediately crash into? Well, it all comes down to a fundamental intellectual rivalry. You've got to understand, this rivalry is the central tension of AI's entire history. On one side, we have symbolic AI, which is often called good old-fashioned AI. This was the dominant approach early on. It relied on hand-coded rules, strict symbolic logic, and programmers literally trying to manually write out every single rule a machine might ever need to navigate the world. On the other side, you have the underdogs, connectionism. Now, this approach proposed building artificial neural networks that would learn patterns directly from data, instead of just being fed top-down rules. But for decades, the symbolic AI camp held all the funding, all the power, and connectionism was pretty much completely dismissed.
And that sets the stage for Section 2, the freezing AI winters. Because those early researchers overpromised on what their rule-based systems could actually do, the industry eventually had to stare into the abyss. The funding dried up, and this brilliantly illustrates the core problem: combinatorial explosion. That phrase comes directly from a devastating 1973 report by James Lighthill for the UK Science Research Council. Lighthill exposed a fatal flaw in symbolic AI. He showed that while hand-coded, rule-based systems worked perfectly fine in controlled laboratory games, like chess or checkers, they completely broke down when faced with the infinite variables of the real world. The sheer number of possible combinations in a real-world task simply exploded way beyond what early algorithms could ever compute. So what did that combinatorial explosion actually look like in practice? It resulted in massive, incredibly expensive geopolitical failures. It really shows us just how fragile tech funding can be when reality doesn't match the hype. During the Cold War, the US poured tons of money into machine translation, hoping they could automatically translate Russian documents. But the nuances of human language just couldn't be reduced to simple symbolic rules. The translations were laughably poor, and funding got completely slashed. Later, in the 1980s, Japan invested millions into this super ambitious fifth-generation computer systems project, trying to build massive parallel logic computers. That, too, resulted in widespread commercial failure. Governments suddenly realized they were overpromising on capabilities like expert systems and automated translation, and they forcefully pulled the plug. For a while there, AI essentially became a dirty word. Quickly comparing these historical deep freezes reveals a very clear pattern. You have the first AI winter from 1974 to 1980, which was directly triggered by the Lighthill report and those Cold War translation limits we just talked about. Then you have the second AI winter from 1987 to 1993, driven by the collapse of rule-based expert systems and the total failure of Japan's massive fifth-generation project. Why does understanding this history matter to us today? Because it teaches us one absolutely crucial lesson: scaling bottlenecks. Specifically, the inability to handle complex, real-world data at scale consistently killed early AI progress. But the story doesn't end in the winter. The thaw finally arrives in Section 3, Deep Learning Changes Everything. Let's trace how this massive structural shift actually happened. Remember those persistent connectionist underdogs? The ones who believed in neural networks and learning from data? Well, they were quietly working in the background for decades. Following Alan Turing's 1950 paper and that Dartmouth conference in 1956, Arthur Bryson and Yu-Chi Ho introduced something called backpropagation in 1969. Basically, this was a mathematical way for neural networks to learn from their own mistakes. But here's the crazy part. That incredible theoretical groundwork laid completely dormant for over 40 years. It wasn't until the 2010s that the convergence of massive GPU computational power and the sudden explosion of big data finally provided the raw fuel required to make backpropagation actually work at scale. Now, what's really interesting about this slide is the year 2012. If you want to point to the exact moment the AI winter permanently ended, this is it. That year, a deep convolutional neural network named AlexNet was entered into ImageNet, which is this massive global computer vision competition. And AlexNet didn't just win, it completely crushed the traditional rule-based algorithms. This massive victory by AlexNet catalyzed the entire modern deep learning boom. It proved once and for all that if you had enough data and enough computing power, a neural network could teach itself to identify images far better than any human programmer writing manual rules ever could. This single event marked the definitive climax, the absolute total victory of data-driven neural networks over the old hand-coded symbolic logic. The connectionists had officially won. Which brings us to the tools we actually use today in Section 4, the modern era of AI. With deep learning totally validated, the pace of innovation just skyrocketed, and that led directly to a monumental breakthrough in 2017. Researchers at Google Brain published a highly complex, absolutely groundbreaking paper called Attention is All You Need. It introduced the transformer neural network architecture. It's a bit dense, but let's break down how this works into 3 simple steps. Step 1. Unlike older models, transformers can ingest massive amounts of data in parallel, utilizing all those GPUs. Step 2. They apply what are called attention mechanisms to evaluate the context and the relationship of every single word in a sentence simultaneously. Step 3. This deep contextual understanding allows them to power incredibly accurate generative output. By mastering these attention mechanisms, researchers finally solved the scalability limits that had caused the AI winters of the past. It was a real game changer. Because of that specific transformer architecture, we have officially entered the era of generative, goal-driven, and agentic AI. The large language models, the ChatGPTs, the systems that can literally write code and generate art for us, they are not overnight successes. As you've seen, they are the ultimate resolution of a 70-year intellectual battle. They represent the final triumph of neural networks, massive data scaling, and raw compute over the old limitations of hand-coded human logic. So as we wrap up this explainer, I want to leave you with a bit of a provocative thought. We now know for a fact that scaling limits and combinatorial explosions caused 2 devastating AI crashes in the past. Today, we are scaling data and compute at an absolutely unprecedented rate. But are we truly immune to a 3rd AI winter? Will we hit a new physical limit with our current hardware? Or will AI just keep accelerating indefinitely? Understanding this historical roller coaster of peaks and deep freezes is the only true way to navigate whatever comes next. Thank you so much for joining me, and keep learning.